Welcome to Chapter 2 on computer arithmetic and digital logic. So now that we've talked about and introduced the computer, explained how it operates on data stored in memory, and talked a little bit about those processes, it's time to dig into how we represent information and digital circuits. Because these topics have important implications on further information that we're going to cover in this course. The way that we represent information, whether it's numerical, textual, multimedia like speech and video, has profound implications on the architecture of the computer. And the representation of numbers determines the type of operations that computers can execute and the way in which data is transferred from place to place, as well as how we store those elements. So in this chapter, in chapter 2, we're going to examine how that information is represented by strings of ones and zeros, and in particular, we look at the representation of numbers and the way in which numbers are manipulated. And I've broken this chapter down into much smaller bites because some of you may not have as strong of a math background necessary to really tackle the computer arithmetic section. And so I want you to take it slow, right? Take a little bite, take it in, do the activity, come back, do the next. So before I jump in, right, we use the term computer without any fear of ambiguity because for decades, we've had to prefix computer by either analog or digital to distinguish it between two entirely different types of computers. And some of you may not even be familiar with an analog computer. But in this section, right, we're going to talk about why computers are digital, why computer designers have universally adopted the binary system, and how information is represented inside of the computer. So we're going to talk about bits and bytes, which you may already be familiar with, and that's great. Before I really dig into this, though, I want to stress the biggest question I usually get when discussing this topic is, well, why do we do it this way? And really, I want to stress that there's nothing magical about binary numbers and binary arithmetic. Digital computers and binary arithmetic have arisen because the corresponding technology is cost-effective to produce. Computer arithmetic is the same as everyday arithmetic, right? If you have 7 apples and you eat one, you have 6 apples. So whether you use decimal arithmetic, count on your fingers, slide beads on an abacus, or use a computer, the result is going to be the same. So you may be familiar with the bit. This is the smallest quantity of information that can be stored and manipulated, right? We can see here that that's a contraction of the words binary digit, right? A bit. And a bit can take a value of 0 or 1, and it's indivisible because it cannot be subdivided into any smaller unit of information. So this is why we say this is the smallest quantity of information that can be stored and manipulated. Digital computers store information in their memories in forms of groups or strings called words. And right, we talked a little bit about words in the last chapter when we talked about registers, but we could think about an example like if you had 0, 1, 0, 1, 1, 1, 1, 1, 0, right? That would be an 8-bit word because there were 8 bits in there. And by convention, we write binary strings with the least significant bit at the right-hand end. And you may have done some binary conversion before in your intro to programming class and maybe really kind of already have talked about this, and that's great. Having a fundamental understanding of binary really helps in this section, but if not, you might need to supplement a little bit to make sure that you really get what we're talking about. But let me see if I can explain, right, a little easier, how computers work. So if computers operated in decimal arithmetic as we do, we could employ arithmetic used in our everyday lives to build a decimal computer that would require electronic circuits capable of storing and manipulating 10 decimal digits. Because most of us do base 10. I mean, humans decided to do this because we have 10 fingers, right? And in computing, we always start at 0. So that would be 0 through 9. But remember, there's nothing inherently magical about the binary system. We can't build low-cost circuits that can reliably distinguish between 10 different voltage levels. And that's what it comes down to. We can build low-cost electronic circuits capable of distinguishing between 2 voltage levels, and we call one of those 0 and one of those 1. And that's why we do it, right? There's nothing inherently magical. Maybe later, maybe sometime in your lifetime, we will figure out how to create circuits that can differentiate between different voltage levels, and we will be able to create a different system on that basis. But computers don't typically operate on a single bit at a time. They operate on our groups, right? Groups of bits. A group of 8 bits is known as a byte, right? B-Y-T-E. And today's microprocessors are byte-oriented. So they can do 8, 16, 32, 64, or even in some cases, 128 bits. And our word, right? Remember our word. A word is described as being 2, 4, or 8 bytes long because the bits can be formed into 2, 4, or 8 groups of 8 bits, respectively. So in general, the more bits a computer can process at once, the faster it is, right? Obviously, the more information that flows through there and the faster we can process it, the faster a computer goes. As computer technology has grown, both more powerful and cheaper, the groups of bits processed by a computer have become larger, right? And the first microprocessors in the 1970s could deal with only 4 bits at a time. And by the early 1900s, we had 64-bit microcomputers that were entering the personal computer market. And today, we have GPUs on graphic cards, which are extremely similar, and they can process 128 or 256 bits wide. And so some computer manufacturers employ the term word to mean a 16-bit value as opposed to a byte, which is an 8-bit value, and a long word to mean a 32-bit value. Other manufacturers are going to use the term word to refer to a 32-bit value, and a half word to refer to a 16-bit value. But throughout the text, and to make sure that we don't have any ambiguity, we're going to use word to mean the basic unit of information operated on by a computer. So let's take a look at this figure as we discuss bit patterns. So I said that a string of bits can represent any data element, and it's quite natural to then think about how many bits would it take to represent a data element. So for example, if we wanted to represent the hour of the day electronically as one of 24 different values, right, 0 to 23, how many bits would we need? And how do we assign bit patterns to those numbers? So let's take a look at this figure here. This is a nice binary tree that demonstrates how we can generate a sequence of binary values using 1 bit, 2 bits, 3 bits, and 4 bits. So starting on the left-hand side, you can see there where it says start. With a single bit, we can move along the path here, one of 2 paths, by representing the bit in a 0 state, and down represents the bit in a 1 state, right? We can see that 0 or 1. So a single bit provides 2 possible states, 0 and 1. Adding the second bit provides 4 paths from the starting point. So now we have 0, 0, 0, 1, 1, 0, 1, 1, right? We can see that. Adding the third bit generates 8 paths. So now we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 011, 100, 101, 110, and 111. And you can already tell how difficult this is for a human to talk about or to remember, right? And I'm not even going to read that fourth bit out, but we get 16 states, right? From 0000 to 1111. And each time a bit is appended to the number, the total number of paths doubles, right? Visually, logically, we can see this. 4 bits give 16 paths, 5 bits give 32 paths, etc. So an in bit, right, word provides 2 to the n different paths for bit patterns. An 8-bit byte has 2 to the 8, which would be 256 possible values. And a 16-bit word has 2 to the 16th, or 65,536 different values, right? So we can see how this exponential math works in our favor when we want to represent any quantity that we can have up to n values of a binary number. We just need to select the minimum number of bits that we need. This figure also helps us see that an n-bit word can be arranged into 2 to the n unique bit patterns. So this figure demonstrates that for n equal to 1, 2, 3, and 4, what then do the n bits of a binary word represent, right? And the simple answer is nothing, because no intrinsic meaning is associated with a pattern of ones and zeros, right? We have no idea what that means. So how a particular bit pattern is interpreted depends only on the meaning given to it by you, the programmer. So before we jump into binary arithmetic, we're going to talk about binary code in general, right? A little refresher maybe for some of you, before we start considering numeric codes. So what do these numbers mean? Right? Inherently, we can break this down into some of the entities that a word can represent. So we can represent an instruction, right? Was it an operation performed by the CPU, typically represented by a single word in the computer with a 32-bit or longer words. So we could have an 8-bit, 16-bit, right? Employs a sequence of words that represents a single instruction. The relationship between the bit pattern for an instruction and what it does is determined then by the designer of the computer. So when we inherently feed those zeros and ones into the CPU, remember we talked about there's a voltage difference between a 0 and a 1 that we've assigned. And so depending on how your processor interprets that string of 0 and 1s, the sequence of bits could mean add A to B, right? One computer might have an entirely different meaning than another computer. On another computer, it might mean add B to C or subtract A from C, right? So it ultimately comes down to how does that processor, that microprocessor, interpret those values that it turns into those voltage differences, right? It has to do with the internal architecture of that microprocessor. We can also represent a numeric quantity. So a word or a sequence of words may represent a numerical quantity, and those could be represented in many different formats. So we could have a BCD integer, an unsigned binary integer, a signed binary integer, right? There's a lot of different ways that we could represent this numerical format, but the byte, if we took like 10001001 could represent the value like 119 in one system, or 137 in another system, or 89 in another system. So we have to know how that processor is going to interpret our instructions, and then programmers have to perform operations on data according to their type, right? So there's nothing stopping you from multiplying the binary representation of John by the number 8, but we have to know that our microprocessor is going to be able to handle something like that. right? And there's no, as we can see here, there's no intrinsically natural sequence of bit patterns. We can write all of the possible patterns of 3 bits. Our left-hand column here represents the binary sequence that's been universally accepted. The right-hand column would be an arbitrary sequence. And really, it comes down to how is the computer going to interpret the information that I'm giving it? We can also represent a character. So a character is a member of a set of elements called the alphabet. And alphanumeric characters of the Latin or Roman alphabet, so that would be capital A to capital Z, lowercase a to lowercase z, 0 through 9, and the symbols asterisk, hyphen, plus, exclamation point, question mark, right, etc., have been assigned binary patterns so that they can be stored and manipulated within the computer. The computer does not understand letters or characters. It has no idea what you're talking about. It is translated into binary. The computer only speaks binary. So we assign these binary patterns so that they can be stored and manipulated, and we've turned this into a code that's widely used throughout the computing industry so that we can all start to kind of speak the same language as programmers, and we can design computers that are all just kind of going back to standards, right? All designed on the same standard. So we have the ISO 7-bit character code, which a lot of you know as ASCII, ASCII code, which stands for the American Standard Code for Information Interchange. And it represents a character by 7 bits, allowing for 2 to the 7 or 128 different characters. So 96 of those characters are printing characters, and the remaining 32 are non-printing characters that carry out special functions, such as carriage returns, backspace, lines, feed, tabs, right? Things that you think about as like formatting, right? They're non-printing characters. So if you're not familiar with ASCII, you can take a look at the supplemental resource that I've put out there for you to take a look at, to kind of get familiar with what we're talking about, what this looks like. Because computers are byte-oriented, it's typical to convert that 7-bit ASCII value to 8 bits by appending a 0 to the most significant bit. Remember, the most significant bit is on the left-hand side. So you'll see this when you're looking at like ASCII charts, ASCII code charts, you'll see that the 0 is typically appended to the left-hand side if we only have 7 bits. And then finally, images, sound, and video, right? Visual components. We have digital computers that can process large quantities of data that represent sound and still images and video. And if we assume that the average word is 5 ASCII characters and a space, and 1,000 word is 6,000 characters or approximately 6 kilobytes, a digital SLR camera with a full frame sensor can take a raw, unencoded image that's about 30 megabytes each. So in this case, right, they say a picture is worth 1,000 words, but in this case, an image is worth 5,000 times more than 1,000 words. So when we store information, right, a fundamental unit of the image is a pixel, right, picture element pixel, which may be 8 bits if this is a monochrome image, or 24 bits if we're dealing with our 3 primary colors. A high resolution image is more, like in your 4K by 3K kind of pixels. So with moving images, right, video, this gets even worse because video is transmitted as a sequence of still images that are updated like 60 times a second, right, 60 FPS. And so in practice, because both still and moving images are compressed to reduce their size, often by a factor of 10 or more, some images are compressed using different algorithms. So it kind of depends on the type of multimedia or the format that you're using, but these take up very large amounts of processing power because we're doing this operation in real time. We're unpacking that data, reading it, getting those images, showing them at that 60 FPS or whatever the frame rate is. And so it would be reasonable to say that progress in high performance computing technology over the last decade has been driven by the needs of multimedia, right? People want more video content, they want more high resolution images, and so the scale of problems involving multimedia, then we have to think about how do our computers process all of this information as quickly as we need it to. So before we jump into our digital arithmetic and start talking about math, let's talk just a little bit about numbers. So we know what numbers are. They're used to count things, right? 1, 2, 3, 4. These are called natural numbers because they don't depend on mathematics. So when we count things, we use the decimal or the denary system to count things because this base has 10 symbols, right? 0 to 9, corresponding to the number of fingers that we have. And that is the honest truth. Humans do things based on what we're given, right? Naturally. Not all numbers are natural. So we have invented negative numbers to handle bank transactions or the absence, representing the absence of something. We've created real numbers to describe fractions, things that have decimal points or things like 13 over 14. Right? Real numbers express themselves or are divided into rational and irrational numbers, right? A rational number can be expressed as a fraction, right? So, like 7 over 12, whereas an irrational number can't be expressed as one integer divided by another, such as pi or the square root of 2, right? Hopefully I'm not getting you too in the weeds right now with the math. So the modern numbering system, right? I like the slide. The great advance in European history includes the symbol to represent 0, which was introduced in Europe from the Hindu-Arabic world about the 1400s, right? Before the 1400s, we didn't have a way to express 0. Isn't that fascinating? This system represents, I'll get off on a tangent about math. This system represents the decimal numbers by means of a positional notation. So the value or weight of a digit depends on its location within a number. So the value of 6 in 1261, right, is 10 times as great as the value of the 6 in 126. We know this, right? That's pretty basic elementary, ones, tens, hundreds, thousands, places. So as we think about numbers and positional notation, we apply this same concept to binary. So let's take a look at this example here on the slide. It says, in positional notation, the n-digit integer n is written as a sequence of digits in the form of a n minus 1, a n minus 2, a to I, a to 1, a to 0, right? And these digits that can take the form of b values, where b is the base, right? We think about what base that we're using in our numbers. In base 10, right, we can write n equals 278. And so a to 2 is 2, and a to 1 is 7, and a to 0 is 8. Following me? So positional notation can also be extended to express real values by using a radix point, right? A decimal point in base 10 arithmetic or a binary point in binary arithmetic to separate the integer from the fractional part. So the real value in decimal arithmetic, right, would be written in the form of, for the example here, 1234.567. So if we use in digits in front of the radix point and m digits to the right of the radix point, then we can write still in this positional notation and express the value of the number in that positional rotation in the base of whatever b is defined at. And maybe you've done this before. We've talked about decimal, you've got binary, we've got hexadecimal bases. We can employ the same subscripts, right? 10 for decimal, 2 for binary, 16 for hexadecimal, respectively, to indicate the base of a number. And if the number base isn't obvious, then we often, if it is obvious, then we often omit the subscript. But that way, if you see it written that way, you understand what they're talking about. Now, again, I hope I'm not losing you in the weeds here with the math. I'm just trying to explain before we get into the binary part of this, how we read it in this form of positional notation. Computer scientists and programmers are really only interested in 4 different bases because those are the ones computers use: decimal, binary, octal, and hexadecimal, right? And you'll see hexadecimal often written as just hex, right? We're talking about the same thing. The octal base isn't used so much today because we've moved into computers that can process more data, so we don't really see the octal used that much, but the hexadecimal base has 16 digits. Letters capital A through F indicate values between 10 and 15. So if you've done any hexadecimal before, you maybe would recognize like 12CF, right? With the little 16 notation indicates that we're using hexadecimal, and it would consist of digits 1, 2, C is 12, F is 15. Right? So the hexadecimal base is used by people often to express long strings of binary digits and is a little easier format for humans to understand than if we had to write out a bunch of ones and zeros. So this concludes our first section for chapter 2. In the next section, we're going to jump into our binary arithmetic and start looking at our basic integer operations working with binary numbers so that we can kind of understand this format a little better.